Hello all, welcome back to Energy in section 1.3. We finished off yesterday looking at gravitational energy. We talked about kinetic energy the day before yesterday, looking at kinetic energy and the energy of motion being determined by 1/2 of mv squared. Right, 1/2 mv squared to determine kinetic energy. And then we moved on yesterday to look at gravitational potential energy, and we used the formula mgh to calculate gravitational energy. I'm not even going to take up any of the homework from last night because I think it was pretty straightforward. I finished yesterday with a discussion about this concept of mechanical energy. Mechanical energy is equal to the sum of Eg plus Ek. Okay, so mechanical energy is typically about motion. Motion for us basically involves two things, often an object's height and an object's speed. And the two things there are going to impact on the motion of the object, as we've looked at in our unit 1, in chapters 1 and 2, when we were talking about velocities and accelerations and distance falling and gravitation, 9.8 meters per second squared of gravitational acceleration. All these things brought us back to the concepts that relate back to mechanical energy for how high an object is and how fast it's moving. So today I want to continue on into section 1.3. In 1.3, we're just starting off very quickly, looking at some of the things we already know. We've already defined energy. We know that there are the two broad types of energy, energy of motion and stored or potential energy. Right, gasoline has stored or potential energy, and the book on the bookshelf that I talked about yesterday has potential energy because of its location relative to the floor in my office here. So what I know is that different types of energy can be interconverted or transformed from one type to another. Again, we call those energy transformations, and we're going to talk more about energy transformations as we move through our part 1 of this unit on energy, work, and power. So we've already talked a little bit about the law of conservation of energy, right, telling us that the energy in the universe is constant. It's constant because we cannot create or destroy energy, and that when an energy transformation happens, basically I cannot destroy or create energy, so whatever energy went into the transformation is the same as the energy that's got to come out of the transformation. So if I move down to the diver here, right, the diver's up on the platform there, and the diver has no kinetic energy because he's just up there. He is not moving. He's waiting, thinking, focusing, concentrating, but not moving. And while he's up there at a height of 10 meters, he has gravitational potential energy of mgh, right? He is 65 kilograms. He is 10 meters up, and G is 9.8, so he has 6,400 joules of energy. So his mechanical energy is the 0 kinetic plus 6.4 of gravitational. Now, as the diver leaves the platform, and starts to fall, you can see that he's going to accelerate. So by the time he's halfway down, if I calculate his gravitational energy when he is 5 meters down from the fall and he's been accelerating for 5 meters, right, I can calculate, where's the rest of the math for this guy? I can calculate his speed because I know he is halfway down. So his V2, when he's at this point here, V1 was at the top, V2 is when he's halfway down. So I'm only looking at the first half of his motion here. V1 squared, which is 0, plus 2a delta d, where delta d is 5. -5 because acceleration is -9.8. I take a v squared and I get a speed of 9.9 meters per second. Okay, and because I know his speed and I know his mass, I can calculate his kinetic energy, half mv squared. I can calculate 5 meters up, 65 kilograms times g. He has 3.2 kilojoules of gravitational energy, and his mechanical energy has not changed. And then lastly, by the time he gets to the water's surface, he has lost all 10 meters. If I look at his v2 squared equals v1 squared plus 2a delta d, his v2, the speed when he gets to the bottom here now, v2 he's not there, v2 is now at the bottom, v1 was 0, the distance is 10 meters, and he comes out to be 14 meters per second. So if I take his 14 meters per second and put it into my half mv squared formula, I get 6.4 kilojoules is the amount of kinetic energy he has. If I look at how much gravitational he has no height left, so he has no gravitational, so his mechanical still comes out to be exactly 6.4 kilojoules. So I can see that his mechanical energy, as he is falling, is conserved, right? It doesn't go anywhere. All right, and that's it. That's our conservation of mechanical energy. That's the end of our section here on gravitational and kinetic energy together as mechanical energy. If I look at the sample problem for 1.2a, is that right? That doesn't look right, does it? No, it's not 1.2a. I am looking at the camera, which is falling. There's it right there, 1.3a. Okay, so it should be 1.3a. So I've got a 1.1 kilogram falls from a photographer's hands while he's taking a picture, and the camera falls 1.4 meters to the ground. What is the gravitational energy relative to the ground? So I'm just actually going to solve it here. So if I do part A, I can calculate the EG, which is mgh. I know that it's a 1.1 kilogram camera on Earth. Oh, darn it. On Earth, 9.8, and it's got a fall height of 1.4 meters. So its gravitational energy, while it's still in the photographer's hand, in the photographer's hand here, is going to be 15 joules. If I look at B, it says using the law of conservation of energy, what will be the kinetic energy as it hits the ground? So by the time it hits the ground, the EG has become 0. When it was in his hand, it had an EK of 0 and an EG of 15. When it hits the ground, it has an EG of 0 and it has speed, giving it a kinetic energy of 15 joules because the mechanical energy is going to be conserved. And if I know that that 15 joules is equal to a half mv squared, I can go ahead and solve for the speed of the camera as it hits the ground, which will probably not be a good thing, of 5.2 meters per second. Okay. Now, I could actually look at this question from a kinematics point of view and solve it using the kinematics. Let's give myself some room here. If I know that regardless of its mass, right, if I know that the V1 when it leaves his hand is 0 and that the delta D is down by 1.4 meters and that the acceleration is negative 9.8, I can do V2 squared equals V1 squared plus 2a delta D, right? And I will end up with V2 turning out to be exactly 5.2 meters per second again. So it doesn't matter how I solve it, I'm going to get a V2 equal to 5.2 meters per second, but that again just goes to prove our law of conservation of mechanical energy. Right, so I'm going to stop there. There's one problem here, which talks about a ball being thrown up, straight up from the edge of a building, and then it's going to land at the base of the building. Right, and it gives us a whole scenario there. Right, so again, as you're looking at this question, let's get rid of all this for a minute. So here's the building. Oops. Here's the person on the building, and the ball's going to go straight up, and it's going to land down here at the base of the building. Okay, so there's the question, the picture for that practice problem for 1.3a. So let's go back to my note for a minute. It should be 1.3a. So there's practice question 1 that we just saw there. There's a summary at the end there. Again, all of these things, all these sections come with summaries that I think are really, really useful. I would take the time to use them and reflect on the summaries because they help to put in perspective all the different parts that we're talking about. There are some review questions, 1, 2, 3, and 4. And then in our textbook, there are some examples. Again, as the last few times, I'm going to encourage you to do the examples, right? 12, 13, and 14 in the textbook. They go over MGH, and they go over mechanical energy, gravitational plus kinetic. And then there's 4 more questions here at the end of our chapter. And again, these are well worth doing also. Okay, so I'm going to stop there. That will end this section of this particular note. When we come back on Monday, we're going to talk about the efficiency of energy transformations. We're going to talk about the concept of power. And we are going to look at how much it costs for energy. And that will be the end of part 1, and we will have a test on part 1. So probably by next Thursday, Friday, we should be ready for a test on part 1 of this unit. Right, so we've still got to finish parts 2 and 3, and then we will be ready for our electricity and magnetism unit. Right, so we're actually moving through at a pretty good pace. I don't think it's hopefully not overwhelming. It shouldn't be. We're not doing anything, like I said, too crazy in terms of daily work. Just make sure you're staying on top of what needs to be done. Watch your videos, do your homework, keep on top of your ISU because your ISU is coming faster than maybe you want. And I want us to be totally ready for that ISU when the time comes. So if I pop us up here to our hub page, again for the live class that we've got a live class tomorrow. So we got a live class here. It's May tomorrow. Happy May. We've got a live class tomorrow, and then from there, live class tomorrow, and then I've got nothing posted for next week. One day next week, the following week on the Monday, we're going to have our ISU discussion, so that we'd be ready for our test on our ISU here on the 20th. Right, so we've got all this week here. So if we do our 1.3 note on efficiency here on the 4th, we will talk about the cost of energy